Hey everyone! Stack lessons here. MLflow PyFunc models, Unity catalog registration, and model serving trips up a lot of students, so today we're going to make it crystal clear. Let's go! By the end of this video, you'll know exactly how to ship a Databricks generative AI model from a notebook to a production endpoint, using the same three-line pattern every Databricks engineer writes. We'll cover the PyFunc wrapper, Unity catalog registration with 3-level naming, and the 4 foundation model API modes, and we'll name the 3 anti-patterns that get flagged in design reviews, pickle uploads, hand-rolled Docker, and Flask plus Gunicorn, and explain exactly why each one breaks in production. In episode 11, we built DataDino's fossil chatbot as a responses agent on the Mosaic AI agent framework, the chain-wired chat Databricks vector search, and an MLflow trace decorator together, and it worked beautifully in the notebook. But that's where most teams get stuck. How do you actually get that chain off the notebook and into a production endpoint that scales, validates inputs, and survives a dependency bump? The answer is 1 code pattern and 3 anti-patterns you should delete on site. Before we get into the mechanics, let's pin down 5 terms you'll hear throughout this video. MLflow.PyFunc.Python model is the base class U subclass to wrap any Python inference logic into a standard, loadable model. A model signature is the schema declaring the expected input and output types required for Unity catalog registration. The 3-level namespace is Unity catalog's mandatory naming format: catalog, then schema, then model name. Provisioned throughput is a model-serving mode that pre-allocates dedicated compute for a foundation model endpoint with an SLA, and a Unity catalog alias is a mutable pointer, like champion or challenger, that names a specific model version without changing it. Here's how DataDino learned this lesson the hard way. An engineer took the fossil chatbot chain, called pickle.dump on it, and uploaded the resulting file to S3. Production loaded it on a different image, where LangChain had bumped a minor version overnight. The pickles class signature no longer matched the installed library, and the worker crashed at deserialization. Same chain, same code, different container, and the whole museum chatbot went dark. The fix wasn't more engineering, it was deleting the pickle and using the canonical Databricks path instead. The core idea for this lesson is simple: dependency drift, lost lineage, and hand-rolled serving stacks all dissolve once you ship through MLflow, Unity catalog, and model serving. Those 3 services aren't a suggestion, they're a single path designed to work together, and every other deployment approach you'll see in code reviews is recreating part of what these already give you for free. 3 moves, in order. First, you log the model with mlflow.pyfunc.log_model. This captures the code, the dependencies, and the signature as a single artifact. Second, you register that artifact to Unity catalog using the 3-level name, catalog.schema.model. That's where versioning and governance live. Third, you deploy that registered version as a model-serving endpoint, which gives you a scaled REST API with autoscaling and request validation built in. Same artifact, same dependencies, every environment. That's the whole pattern. Here's the mental model. MLflow is the meal kit. It ships the recipe along with every ingredient, listed by exact brand and quantity. Unity catalog is the labeled shelf in a regulated warehouse, where every kit has a known address and an owner, and model serving is the kitchen that rebuilds the exact dish on demand every time a request comes in. The pickle plus S3 anti-pattern, that's emailing someone a photo of your fridge and hoping they figure it out. Let's start with PyFunc, because it's the foundation of everything else. MLflow.PyFunc.Python model is a base class U subclass to wrap any Python inference logic, chains, agents, custom large language model clients, pre- and post-processing code, whatever you've built. When no native MLflow flavor fits your model, PyFunc is the universal escape hatch. The beauty of it is the contract. One artifact, one predict interface, one deployable thing. The framework no longer cares whether the inside is a LangChain chain or a custom orchestration class. From MLflow's perspective, it's all the same shape. Every PyFunc model has this exact shape. Use subclass Python model and implement two methods. Load_context runs once. When the serving worker boots, it's where you grab artifacts and configuration. Predict runs on every request, taking the context and the validated model input and returning a response. That's it. The pattern is intentionally tiny, so the framework can handle everything around it: request routing, validation, scaling, tracing, without you writing any of that infrastructure code yourself. The split between these two methods matters more than people expect. Load_context runs once. At worker startup, it's the place to load artifacts and configuration references, and you want it light. Heavy initialization here delays every cold start. If load_context fails, the endpoint never boots at all. Predict runs on every single request. It receives model input that's already been validated against your signature, and it must be stateless and cheap. If predict fails, the caller gets a 500. The discipline is cheap setup work in load_context, real work in predict. Vector search client and other stateful clients have non-trivial initialization latency. Heavy setup inside load_context delays every cold start, and on some endpoints it surfaces as a startup failure with a confusing stack trace. The more robust pattern is lazy initialization. Hold a none reference in load_context and instantiate the client on the first predict call, behind a guard. This decouples connection setup from endpoint boot, which meaningfully reduces flaky cold starts on real workloads. It's also the pattern teams converge on once they move from notebook prototyping into production serving. Now the signature. A model signature is a schema declaring the expected input and output types of the model. The Unity catalog docs are explicit. New model versions must have a signature. You can technically register a version without one, but you lose a lot. No auto-generated input examples. AI functions can't read the schema, so you have to declare it by hand. And at serving time, the signature is what model serving uses to validate every incoming request before forwarding it to your predict method. Skip the signature, and instead of failing cleanly at deploy time, you get 400 errors at runtime from confused clients. The signature is the contract between your model and everything that calls it. The Databricks docs put it plainly. New ML model versions in Unity catalog must have a model signature. The good news is you don't have to handwrite one. Use autologging, or supply an input example in your log_model call, and MLflow infers the signature automatically, which leads us straight to the next concept. Input_example does 3 jobs for the price of 1. First, MLflow uses it to auto-infer the signature, so you never write a schema by hand. Second, MLflow runs predict against it at log time, which means schema mismatches and runtime bugs surface during logging, not after deployment. Third, MLflow writes out a serving_input_example.json file, shaped exactly like AREST payload, so you can paste it straight into a curl test of the production endpoint. One small sample buys you a contract, a smoke test, and a ready-to-use deployment harness. Here's the log call that ties it all together. Inside an MLflow run, you call log_model with 4 key arguments. The artifact path names the directory inside the run. The Python_model is your fossil chatbot instance. The input example is a sample payload. Here, a simple question about T-Rex extinction, and pip_requirements pins the exact versions your model needs. Notice MLflow is pinned explicitly with a version number, alongside Databricks-LangChain and Databricks Vector Search. That pin is doing critical work, and the next slide explains why. On Databricks Runtime MLflow's automatic dependency inference captures MLflow Skinny, a slimmed-down variant of the client that's optimized for fast notebook startup. Model serving cannot build a container image from Skinny, because it's missing the model loading and scoring modules the serving runtime needs at boot. So your log call succeeds, registration succeeds, and then the endpoint silently fails to build. The fix is one line. Explicitly pin the full ml package with a version number in pip_requirements, not mlflow Skinny, just mlflow. The official documentation could not be more direct. Always specify mlflow with an explicit version, for example 2.16.0, in pip_requirements when you call log_model on a Databricks runtime ML runtime. Model serving requires the full MLflow package, not MLflow Skinny, and cannot build the container image otherwise. If there's one production rule from this entire video worth pinning above your desk, this is the one. Quick checkpoint: we have a PyFunc model, a class with load_context and predict. We logged it with an input example, so MLflow inferred the signature automatically, and we pinned MLflow plus real dependencies, so the serving container can faithfully rebuild the environment. Now the next question: where does the logged model actually live, and how does Databricks find it again when we want to deploy it? 2 lines do the registration. First, mlflow.set_registry_URI with the string databricks-uc. That points MLflow at Unity catalog instead of the legacy workspace registry. In MLflow 3 this is the default, but writing it explicitly is belt and suspenders for any code that runs on older runtimes. Then call register_model with the run URI and a 3-level name, here, prod.fossil_rag.fossil_chatbot. That string is the entire address of the model. Look at what each level does. The catalog is the environment, typically dev, staging, or prod, and accessing it requires a USE's catalog grant. The schema is the team or project domain, like fossil_rag or fraud or rex, gated by a USC schema grant. The model is the artifact itself, which holds versions and aliases, and creating one requires a create model grant. 3 names, 3 permission boundaries. That's why governance feels native instead of bolted on. It's literally baked into the address of every model. Think of it like a postal address. prod.fossil_rag.fossil_chatbot tells you the environment, the team that owns it, and the specific model, all in one glance. A flat name like fossil_chatbot is just a sticky note. There's no environment, no ownership, no way to grant prod access without granting dev access. The 3 levels turn naming into routing. If you've worked with the old workspace registry, this is a real shift. Before, you had a fixed lifecycle: none, staging, production, archived. Each version transitioned through stages as a real operation, and that whole registry has been deprecated for new accounts since April 2024. In Unity Catalog, that's gone. Instead, you get mutable aliases, names like at champion or at challenger, and you reference a model as models/catalog.schema.model at alias. Promoting version 17 to champion is now a metadata flip, not a rebuild. Version numbers and deployment slots are completely decoupled. Promotion is literally one method call. Create an MLflow client, then call set_registered_model_alias with the 3-level name, the alias champion, and the version number, here, 17. Every downstream caller is already referencing models/prod.fossil_rag.fossil_chatbot at champion. They never need to know the version changed. That's the entire promotion ceremony. Both flavors exist for a reason, and the decision rule is straightforward. Use mlflow.langchain.log_model when your model is itself a LangChain object, a chain, an agent, an LCEL pipeline. The LangChain flavor knows how to serialize those constructs and gives you predict_stream for free. DataDino's pure LCEL fossil chain fits here perfectly. Use mlflow.pyfunc.log_model when you have custom code, pre-processing, post-processing, guardrails, multi-component orchestration, or a framework MLflow doesn't natively support. PyFunc is the escape hatch when the LangChain flavor doesn't cover what you're shipping. Now let's zoom out to the broader question of how foundation models get served on Databricks. There are 4 modes, and each one fits a specific shape of workload. Pay-per-token endpoints are shared, instant, and prototype-friendly. Provisioned throughput gives you dedicated capacity for production. AI functions are SQL callable and optimized for batch inference over delta tables, and external models proxy your traffic to third-party providers like OpenAI, Anthropic, or Cohere. The right answer is always determined by the constraint, not by habit. Compare the 2 primary modes side by side. Pay-per-token endpoints are shared infrastructure, pre-configured, and billed by tokens consumed. They're governed by queries per hour and tokens per minute caps, both for input and output tokens, and the exact numbers vary by model and workspace tier, so check the Foundation Model API's limits page in the official docs for the current values. Pay-per-token is excellent for prototypes, demos, and low-volume tasks. It's HIPAA eligible when your workspace uses the right compliant security profile, but it does not cover PCI DSS or FedRAMP. Provisioned throughput is dedicated compute with configurable throughput, a real performance SLA, and support for fine-tuned and custom weights. It adds PCI DSS and FedRAMP AMP on top of HIPAA, and significantly higher limits are available on request through your Databricks account team. Picture it this way: pay-per-token is a rideshare. It's instant, there's no commitment, and you can use it whenever, but you're queued behind everyone else, and surge pricing is real. Provisioned throughput is leasing a car. There's a fixed cost, your seat is always available, and you get to install whatever you want, like a child seat, or in this analogy, your fine-tuned weights. Once you internalize that picture, the moment to switch becomes obvious. The Databricks documentation states the rule directly. Provisioned throughput is recommended for all production workloads, especially those that require high throughput, performance guarantees, fine-tuned models, or additional security requirements. When a scenario mentions any of those 4 conditions, the answer is provisioned throughput. The other 2 modes handle very different shapes of work. AI functions, accessed through I_query in SQL, run inference over delta tables. They're optimized for batch, millions of rows scored in parallel, which makes them the right answer for nightly scoring jobs. They're not a real-time request path. We'll go deep on I_query in episode 19. External models is a proxy endpoint to providers like OpenAI, Anthropic, or Cohere. The API keys stored in Databricks secrets, not in notebooks, and you get central authentication, audit logs, and rate limits inside Unity Catalog. Use it when the team needs governed access to a third-party large language model. Here's the decision rule in 4 lines. Prototype or experiment, pay per token, SLA, HIPAA compliance, or fine-tuned weights, provisioned throughput, score a delta table of millions of rows, AI functions, third-party large language model with central governance, external models. The constraint in the requirement picks the mode, not your habit, and not whichever endpoint you used last week. Now to the 3 anti-patterns. Pickle plus manual S3 upload. That's the DataDino crash we opened with. Hand-rolled Docker containers with bespoke inference servers, and Flask plus Gunicorn services hand-built behind a load balancer. None of these are the Databricks native path, and each one fails for a specific, predictable reason. Let's take them one at a time. Pickle plus manual upload fails for 4 reasons that compound. First, pickles bind tightly to the Python version, the library versions, and even class definitions in the Dunder main module. Any drift and deserialization throws. Second, notebook-defined classes pickle into Dunder main and then fail to load inside the serving worker, because the worker has no Dunder main module containing your class. Third, there's no dependency manifest traveling alongside the .pkl file. Drift stays silent right up until the runtime crash. And fourth, you've got no lineage, no signature, no governance. It's just a blob in a bucket, with no record of how it got there or what it needs to run. Hand-rolled Docker is redundant for a simple reason. Model serving already builds and runs the container for you, using your pin dependencies from log_model. It already handles auto-scaling, request validation, MLflow tracing, and log capture. Maintaining your own image means re-implementing what the platform gives you for free, and getting all of it slightly wrong. Worse, your custom container bypasses Unity catalog governance entirely. There's no registered model, no version history, no permission boundary tied to the artifact. Flask plus Gunicorn is the wrong layer of abstraction. You're rebuilding the request layer that model serving already provides. There's no automatic signature validation, so every malformed payload becomes a 500 instead of a clean 400. There's no native MLflow tracing, no Unity catalog permissions attached to the endpoint, and no platform-managed auto-scaling. You inherit a pile of operational work, patching base images, tuning workers, managing TLS, that the platform was specifically designed to absorb for you. When you're designing a serving path, you have a few tempting shortcuts and one scalable pattern. Pickling the chain to a volume or S3 breaks the moment a dependency drifts, because the unpickled object expects exact library versions you no longer control. A hand-rolled Docker image re-implements the model loader, the scoring server, and the autoscaler that model serving already provides. Flask plus Gunicorn behind a load balancer adds an operational layer for the request path the platform handles for you. And a Spark UDF wrapping chat Databricks fails at executor serialization, because Cloud Pickle cannot move a live foundation model client across the cluster. The canonical path, log with PyFunc, register to a 3-level Unity catalog name, deploy as a model serving endpoint, and use a I_query for batch scoring, eliminates all 4 sources of friction. Deploying the endpoint is a single call to create _endpoint, and the config has 4 knobs worth knowing. Entity name is the 3-level Unity catalog model you're shipping. Entity version pins the exact registered version, or you can point at an alias instead. Workload size picks the concurrency tier, small, medium, or large, and the endpoint auto-scales within that tier. And scale to 0, when enabled, drops idle endpoints to 0 cost and cold starts them on the next request. That config block is the whole deployment. The platform handles container build, auto-scaling, request routing, and signature validation for you. Here's the payoff for providing input_example at log time. The serving_input_example.json file MLflow generated is already shaped like AREST payload. You curl it straight at the production endpoint's invocations path with your bearer token, and the endpoint returns a predictions array. The Tyrannosaurus Rex response confirms the chain ran end-to-end. Same artifact, same dependencies, same predict method, just running on managed infrastructure instead of your notebook. 4 production issues worth remembering. Inline helper functions defined in notebook cells pickle into Dunder main and fail to load in the serving worker. Put them in a .py module and pass them through code_paths. Integer columns with nar_ns become float at serving time, so declare them as double in the signature upfront. Forgetting set_registry_URI on older runtimes silently lands your model in the deprecated workspace registry. And wrapping chat Databricks inside a Spark UDF fails because Cloud Pickle cannot serialize the active client, For batch foundation model work, use I_query instead. Drill these 3 lines until they're muscle memory. Log with mlflow.pyfunc.log_model, providing an input example and pinning mlflow alongside your real dependencies. Point the registry at databricks-uc and register under a 3-level name, catalog.schema.model. Deploy as a model-serving endpoint, picking pay per token for prototypes or provisioned throughput for production. And remember that pickle plus S3, hand-rolled Docker, and Flask plus Gunicorn are red flags in any Databricks code review. Now let's see how well that pattern stuck with a quick 5-question quiz. Alright, time to put your knowledge to the test. Question 1. An engineer has built a custom retrieval chatbot on Databricks and needs to deploy it to production. Which approach follows the canonical Databricks deployment path? Is it A. Pickle the chain object, upload the .pkl to a Unity catalog volume, and load it from a Flask service running on a job cluster? B. Subclass mlflow.pyfunc.python model, log with input example and pinned pip requirements, register to catalog.schema.model in Unity catalog, and deploy as a model-serving endpoint. C. Build a Docker image with a Gunicorn server wrapping the chain, push it to a container registry, and deploy it behind a load balancer. Or D. Save the chain weights to S3, write a custom REST API in Fast API, and deploy it on a Databricks apps workspace. Take a moment to think about it. The answer is B. The canonical Databricks path is mlflow log_model, Unity catalog registration with 3-level naming, and model-serving deployment. The other 3 options are explicit anti-patterns. They bypass governance, lose dependency manifests, or rebuild what model serving already provides for free. Question 2. A team logs a PyFunc model on a Databricks runtime ML cluster without specifying pip requirements. Registration to Unity catalog succeeds, but the model-serving endpoint fails to build. What is the most likely cause? A. Unity catalog requires an explicit catalog name in the pip requirements list. B. Model serving cannot deploy PyFunc models without an MLflow run name. C. MLflow auto-captured MLflow skinny from the runtime, and model serving cannot build a container from lflow skinny, only the full LLflow package. Or D. The model serving endpoint requires a separate workload type parameter that pip requirements supplies. Take a moment to think. The answer is C. On Databricks Runtime ML, MLflow's auto-inference captures MLflow skinny instead of the full lflow package. Model serving cannot build a container image from skinny, so the fix is to explicitly pin MLflow with a version number in pip requirements. Question 3. A healthcare company is deploying a clinical notes assistant that must meet HIPAA compliance requirements and a strict latency SLA. Which foundation model API mode should they choose? A. Pay per token endpoints, since they offer the lowest startup cost. B. Provisioned throughput, because it provides performance SLAS, dedicated capacity, and HIPAA eligibility. C. AI functions via I_query, since they're optimized for low latency single row inference. Or D. External models, since HIPAA workloads must always be routed through a third-party provider. Take a moment. The answer is B. Provisioned throughput is the only mode that provides a performance SLA, dedicated capacity, and HIPAA eligibility, along with PCI-DSS and FedRASS and FedRAMP. Pay per token has no SLA. AI functions are for batch over delta tables, and external models proxy third-party APIs without changing the underlying compliance posture. Question 4. A team wants to promote version 17 of their model from a challenger slot to the production serving slot in Unity Catalog. What is the correct way to do this? A. Call client.transition_model_version_stage with stage equals production on version 17. B. Relog the model, increment to version 18, and tag it as prod. C. Use client.set_registered_model_alias to point the @champion alias at version 17. Downstream callers reference model/catalog.schema.model @champion. Or D. Copy version 17 to a new catalog called production and update the endpoint configuration. Take a moment. The answer is C. Unity Catalog replaced the old stages with mutable aliases. Promoting a version is a single set_registered_model_alias call. Version numbers stay constant, and downstream callers reference the alias rather than the version. There is no staging or production lifecycle in Unity Catalog anymore. Question 5. Let's test a concept from an earlier episode. In episode 11, DataDino's fossil chatbot was implemented using which Databricks agent base class for new agent development? A. Chat agent, since it's the only base class that supports MLflow tracing. B. Responses agent, the current canonical base class that is wire-compatible with the OpenAI Responses API and supports auto-inferred signatures. C. Python model, since all Databricks agents must subclass mlflow.pyfunc.python model directly. Or D. Genie agent, since it's the recommended base class for any RAG agent on Databricks. Take a moment. The answer is B. Responses agent is the current canonical base class for new Databricks agents, wire-compatible with the OpenAI Responses API, with MLflow automatically inferring its signature. Chat agent is still acceptable for existing agents, but is superseded for new work. Genie agent wraps Genie spaces, not arbitrary retrieval augmented generation. And we're done with MLflow PyFunc models, Unity Catalog registration, and model serving. If this saved you a wrong answer on exam day, hit subscribe. The Databricks GenAI Engineer Cert keeps going, and I want you to pass on your first try. See you next time.